This is an overview for the second half of the midterm one practice exam dealing with acids and bases. It's going to be helpful to have a plan and understand what's going on with all of these different scenarios, whether we have strong acid or base, weak acid or base, salts, when we have a polyprotic scenario, when we're dealing with conjugates like HCO3 minus, very dilute strong acids and bases, very dilute weak acids and bases. So this is the order that we address them, that Atkins covers them. So you want to have a plan to be able to recognize each of these and execute it. Here would be an example. As I look within this one, I'm seeing a salt. I see a Kb value listed for ammonia. So my plan within this one, I'm going to write out the ammonium cation behaving as an acid. I have a Kb value listed for ammonia, so I can get a Ka value for the ammonium. Run that through my ice table, neglect X within the initial analysis. I see that X is a very small number relative to the 0.25. When I've solved for X within this one, that's the hydronium. So I'll take a pH of that and concentration, and sure enough, by taking the salt, we find that it ends up being acidic. As I look within this one, I see a Kb value. I'm going to run this one straight as a weak base. Set up my ice table, set up the Kb expression. See what happens if I neglect X. Once again, it's very small to the initial concentration. That's good to go. In this case, I'm solving for hydroxide. I got a pOH value, converted that to a pH. This one, we're looking at aspects of molecular structure. Within Atkins, we saw a couple different ways to explore and describe it for these binary acids. This description of what happens when we moved across the row where the electron affinity was an important variable, that would allow me to compare aspects of the HF and the H2O. And then if we were going down a row, that would be HF and HCl. And so Atkins within this one was looking at aspects of bond strength. So for each of these, we could have a structural description, what's taking place within the molecules and how that's affecting the pH. One other thing that I added to this one is my own description of how I oftentimes make sense of this, and this is a nice way to extend it if I'm thinking about the oxyacids or if I'm thinking about the role of resonance, considering the stability of the conjugate. And instead of asking the question, tell me about what does it mean to donate a proton, to ask the question, once we've created the conjugate, do we see the reverse process taking place? So if I'm able to take the charge on my anion, spread it out there, make it more diffuse, it's less likely to react and have the reverse process take place. So all of these are ways that we can begin to think about and explain how the structure is affecting the strength of the acid. Calculate a pH for sulfuric acid. I notice within this one only one Ka value is listed because the first donation of the proton is very strong. Ka sub 1 would be a huge number for us. So we can take that and consider it to initially dissociate, and based on the stoichiometry, I have an initial value for the conjugate and an initial value for the hydronium. I'm going to put that into my ice table for the expression that I would use for Ka2. If I run that one through, we might ask, well, can I neglect X? Well, the math on it's easy. If I neglect X, I'd be neglecting the plus X and the minus X. So that would be 0.095 over 0.095. I can do that in my head, and I find that I would have an X value then equal to this Ka sub 2 value. If I compare that with respect to the concentrations, it's about 10%. So no, I definitely can't be neglecting X in this case. So the setup within this one, if you showed the work here and discussed this, that's fine. I don't need you to continue on and solve the calculation. This setup, this discussion is satisfactory. If you're curious, this would be going through and solving for x within the equation, and we see it's a quite acidic solution. Within here, we're looking at the composition for a weak acid and a strong acid, both with the same initial concentrations. So I want to think about how my the two within here, I see that I got a typo, sorry about this. I'm describing HA as being a strong electrolyte and HX as being the one in equilibrium. So I have that part backwards within that. So please hang with me on that part. If I'm thinking about the one that dissociates and is strong, well, I'd have water in the container within the beaker that would be much, much greater than the two species that I see as my strong acids dissociated. But those would be equal to each other based on the stoichiometry, and I still have some hydroxide present based on the Kw. If I'm looking at the one in equilibrium, and once again, sorry for reversing that notation, I'd have a lot of water within the beaker. The next would be the weak acid molecule, which would be greater than the hydronium or its conjugate. Those would be equal to each other based on the stoichiometry. And I've got the smallest amount would be the resulting hydroxide, which I have based on the Kw. If I were to compare each of these, I would see that I could make comparisons on the hydronium concentration. It would be higher for the strong acid. I could think about the comparisons involving the conjugate. It would be greater for the strong acid. And I could do comparisons based on the hydroxide, which would be smaller for the strong acid. So that's my analysis within each. And once again, I apologize for mixing up my HA and HX in my worked example here. For using this figure to discuss various concepts involving pH, pOH, and Kw, I think essential in this description is our description of what Kw means. Kw is an equilibrium constant for water. It has a temperature dependence. It's telling us the concentration of H plus and the hydroxide. So any spot along this red line, that equation is applicable. Now we could convert that because H plus and hydroxide within here oftentimes are really small numbers. So if we take our negative log within this, that turns it into the P scale. So we could use that for the pH, the pOH, and relate that to the pKw. So within this one, the kinds of topics that I would want you to be able to connect, well, why do you always have both a concentration for the hydronium and the hydroxide? What does neutral mean within this description? What is the role of Kw? And why are we using this P scale? Those would all be things to potentially discuss. Within this one, we have some data involving the hydration of the A- anion. What's taking place? How does this fit into potential trends describing the behavior of these acids? So I'm coming to this description right here to think about, well, what is the step that's being described right here? So this step is looking at the hydration of our conjugate that we formed. So we want to be able to think about the role of the various steps within here, why we took it to being gaseous in the first place. This step right here is exothermic, and the greater the overall delta H, the more likely the process there is resulting in a stronger acid. I say more likely because we have the caveat here that entropy can also play a role. And as I look within this one, I see that it's not a great fit here when we're looking at the enthalpy involving the hydration. The hydration is taking the conjugate, it's getting surrounded by the water molecules. That's an exothermic process as I have this coming together. And I see that it's more exothermic for the molecules that I have here that are not stronger acids. So in this case, it's not a great variable that I would use to explain the trends in the acid strength. The strongest acids have the greatest overall exothermic values, and that is not being explained by this feature. Here we have the acid H2A, various pKa values listed. This would be the sketch that I would make. I know that I have a 50-50 between H2A and the conjugate HA minus at that first pKa value, a 50-50 in the composition at the second pKa value. The greatest amount of HA minus is at the 1/2 the pKa values. I see these very steep slopes in each of the cases. Key things that I'd be initially looking for is how do I use those pKa values and relate them to aspects of the composition. Putting these in order based on pH, I think it would help to classify them first. So I have a strong acid. I'd be seeking to explain that has the lowest pH. I have two different ones that would be serving as weak bases. Ammonia is a weak base. Sodium fluoride is a weak base because the HF is a weak acid, and here I'm thinking about the conjugate in that salt. For both of those, I sort of need some data, okay? It's fine to describe how both of them are going to behave as weak bases, but if you say that in order to rank those, you need additional data, which would be the Kb for the ammonia or the Ka for HF, and how you would use that to get a Kb for the fluoride, that's a fine description. And then water, its pH would be dictated by the Kw. When we're thinking about the Kw, if I'm looking at these different descriptions and what would affect the pH calculation, for the sodium chloride, in a sense, the Kw is important in that. Because if I'm thinking how the cation and the anion are not affecting the pH, because neither of which is acting like a weak base or a weak acid, we might then ask, well, what would be affecting the pH? Well, the pH in that case is affected, it's calculated based on the Kw value. So is it important or not, the autoprotolysis of water? In a sense, you could say it is important because that's what's leading to a value of pH 7. If I'm looking at acetic acid here, pH is going to be much less than 6. So that will be dominating my pH analysis. I don't have to worry about the autoprotolysis of water because my pH is not near 7. If I take this example here, though, of a very weak, strong base, my value is not just near 7, it leads to this absurdity that I'm taking a base value. If I take a POH, it's such a dilute concentration that it ends up telling me that it's an acidic solution. And I know that can't be right. So if I'm working through that one, I would set it up and I would treat it as if I have a common ion. I have an initial head start on the amount of hydroxide that I'm going to take from the sodium hydroxide solution. I put that as an initial quantity for my hydroxide, run that through my ice table, and then I have equilibrium values that I could now put into the expression for Kw. Solving for X would be solving for the hydronium concentration. Take the negative log of that. That would give me the pH. This description right here, this would be very complete. Once again, you wouldn't have to solve for X within this one. But this could support your analysis how the hydroxide concentration for this very dilute strong acid was being affected by the fact that the hydroxide simply coming from the Kw was going to be an important factor, because our hydroxide, if we did not include the Kw, was giving us too low of a value, so we needed to incorporate the contribution from Kw to figure out what the actual concentration for the hydronium and the hydroxide was.